Any thoughts about that? Is that kind of what we just did? Does that feel like what we just did with that first problem? I might have time together. Let's. So some of these I might kind of skate over some details. We're going to work on this today and tomorrow. You might be thinking, like, can't we do in this period and tomorrow all 7 of these problems? The answer is, like, probably no. So I don't know. But I love them all, so it's a little bit hard for me to say that. What's up? We good on that? Let's just spend a second to try and set this up, and maybe I'll leave the calculus for you on this one here too. But let's at least try it. Take a second to set this one up. Maximizing area again, right? Yeah, you need a picture of that in your mind here. What does that look like?
Oh, so it would be 2x, and that's the value of 1. That's the little
Well, yeah. Yeah, like, so when I purchased my December 15th tickets for Star Wars, I think you do the same thing.
like that's the
right? You don't think the front row. Very narrow also very narrow. There's some optimal spot. You get the maximum not here, not here, but somewhere right in the middle. So the optimal X, Y. But if I were designing a museum, I really want to put all the bench here.
Do not make me actually like so right. Or it could be like, I don't know, I want to be exactly right? When you go along to these, so it would be 2x.
We should go do that analysis. We should also actually piggyback on the ball sheet.
That's X, or you should say it's now get 2x.
Or just check the Y. Take a look at that right. Is this one up? And then we take a red line and say, this actually is the exact
24x minus.
That's true. So we need optimal placement with the next thing. All right. Did I give you a chance to struggle with this a little bit? Here's the picture, right? All right, yes? Am I right? Okay. These are not real nice values, I guess. Huh? Doesn't matter though, really. Okay. That's 12 right there. So well, here's the thing we don't know. We don't know what this is. So maybe let's let that be x. Right? We don't know what that rectangle is. This is a fixed curve under which we're putting a rectangle. Is that the picture? I want to make sure we're all on the same page here.
I got it.
And we're not sure what this x should be, but once you've decided on this x, everything else is determined. Like if you know that if this is the distance you need, well then clearly the whole side will be twice that, and this will go up here and meet the function, and you've got your rectangle. But we're not sure which rectangle. It could be a rectangle that's tall and skinny, could be one that's like real short and all the way across and fat, right? So somewhere in there, in fact, you can even feel the optimization, can't you? Like if you choose an x that's really big, you're going to get like no area, pretty much. And if you pick an x that's too small, you'll basically get no area. You'll get like a tall, skinny rectangle with virtually no area. Somewhere in the middle is like the optimal x, the choice of x. Right? You can feel the optimization. All right, so we need an area formula for this rectangle. It'd be nice to know perhaps like what the coordinates of this point are. It's x comma y, or 12 minus x squared, right? That's the coordinate of this point. X comma y, or if x is x and y is 12 minus x squared. So, can you give me the height of this rectangle in particular? I guess we just said it. What's the height? 12 minus x squared. What's the width? 2x. All right, so now we're ready to say what the area is. It's 2x times 12 minus x squared. Optimize. Okay, right? Figure it out. Now, the other thing that we need to be careful of, just like on the last problem with the fence, you need to be really careful of to answer what was asked, right? So in this particular case, what's your final answer going to be? What is the largest area the rectangle can have, and what are its dimensions? So you're going to give both 2x and 12 minus x squared. Once you find the optimal x value, notice that like reporting what x is not the answer to this question, right? Reporting whatever x times 2 is, and whatever 12 minus x squared. Those are the dimensions. And then also reporting the area. Those are the things we're looking for. Okay. Should we? Okay. Like I said, is it worth going? Maybe we want to. I don't know. You want to go through this real quick? Let's see if we can. I don't know. Maybe it's a bad idea, but we'll work it the way through here. What are we doing next? Of course, take the derivative. So 24 minus 6x squared equals 0. So what do we get here? X squared is equal to 4. X is equal to plus or minus 2. But of course, in the context of the problem, it makes sense that we'd be thinking about x equals 2 perhaps. So like we can easily see why x equals -2 is also an answer. All right, but again, that's not the thing we're boxing. What are the dimensions of interest that optimize? Well, again, we also need to ensure that this is in fact a maximum, x equals 2. So you want to use the second derivative again? What's a double prime? -12x. And if x is 2, that is a double prime of 2 is -24, which is less than 0. So that's definitely a maximum. You see how I'm using the second derivative test? I just like it a little better than having to do the number line on this stuff. The number line is great when we have to like kind of identify intervals and like a lot about the function. But if we're only checking at one value, hey, is this a max or a min? The second derivative test becomes pretty handy. So this is because a double prime at x equals 2, a double prime is negative. This is definitely a maximum. Okay, so what are the dimensions? What are they? 4 and
8.
Yeah, 8. So 8 by 4, and the area is then.
Why 8 by 4?
I don't know. I just trusted you.
Because 4 by 8.
You're 8 by 4, 4 by 8, whichever. 4 by 8. 4 wide, 8 high, and 32 units squared is the area, I guess. Yeah.
So what would be the difference if we were trying to minimize the area?
Well, the minimum of the area occurs at 2 places. At x equals the square root of 12, and at x equals 0. You'll see if you like work this out here. If you're trying to find the minimum of this, you'd have to consider the endpoints of the domain. The endpoints. You get 2 minimum values and they're at endpoints. But I don't think anyone would want to minimize the area because the minimum area is 0.
Because sometimes they ask like, can you minimize or maximize, just like on the homework, and I couldn't tell if there was a different equation to use for minimize.
Yeah, they might ask you that, and then you might be looking at endpoints, right? Yeah, so you just need to be aware that this function only makes sense on the interval x between 0 and root 12, right? That's like the domain of this area function. Do you agree?
Sure.
Right, like the area, this only makes sense if x is some number between 0 and the square root of 12.
Yeah.
Outside that, now we're like on this other part of the parabola, and like, right, we're done. So it turns out that on this closed interval at 0 and 12 you have minimums. And in both places, the area you get at both of those places is 0. So it's not very interesting, but there's your answer. Okay. Again, let's maybe just set this one up and then move on. We won't do the calculus on this one here. Really, the pre-calculus is a big task on all these, believe it or not, right?
Wait, didn't we finish
Calculus.
number two?
Yeah.
Okay, I
We
thought
did.
just
I know. I
that.
said, but then I got, we got carried away, and we just decided to do it. This one, I promise, we're not going to do all the way.
No.
I can't. Please do this one. It seems harder.
Yeah, we are.
It's real hard.
You mean the calculus part? No, the setup is the hardest part. I promise. I promise.
What do you mean? No, the easy.
I promise. No, I think you maybe have it set up wrong. Here's the picture here. We've got a closed box with a square base. Here's the picture I would draw. Right? Something like that. Why? What's that? That's the net of that box. It says find the dimensions of the box that will lead to the minimum, this time minimum total cost. Eventually I want in my possession a cost equation. And the cost is really a function of the surface area, right? Each piece of the box is going to cost a different amount. The volume doesn't have very much to do with that really, even though the volume is given. So if we call this, it's a square box, so let's call this base x by x. Is that cool? And then the height we'll call h for now, so we can just band with it. The volume is then, how does that, can we relate those variables? 1600, sorry, 16,000. So I get an extra 0 in there. There we go. Is inches cubed, which is equal to inches cubed. Okay, is equal to what? Yeah, the volume of that box is x squared h. X squared h. Okay, so that's worth mentioning, but eventually that's not what we really care about. What we really want in our life is a cost equation. So let's start working on one. And this is where this picture comes in handy. Start labeling some distances on here. This side is x and x. This side is h. So is this, even though my drawing's not that good, right? You can label as much or as little of this as you like. And down here, this is also x by x. Okay. Now, I haven't even read the question yet. It says the material for the top and bottom of the box costs $3 per square inch. So how much does this square right here cost? It's got an area of what?
X squared.
Let's write the areas here. This one's x squared, this one's x squared here. I should use another color or something, sorry. This is xh. This is xh, xh, and xh. But we still didn't answer the question here. What's the cost of this piece? Its area is x squared, but what is its cost? 3x squared, yeah. And the cost of this? It says top and bottom, also 3x squared. So the cost is, for the top and bottom, is 6x squared. All right, what about the four sides? That's a total of 4xh, but each one of those is 150. So 150 times 6xh. So that's, I think, our cost function. You see how we got that? That's the hardest. I think that's the hardest part of the problem.
4x? Yeah.
Sorry, 4h. And I think that's the hardest part of the problem. I think the calculus part is not that bad. But we're not really ready to do the calculus step. We'll do one more pre-calculus step. Because right now we have a cost function, beautiful, and it's correct now. But it still has two variables, two independent variables. But what haven't we used yet that we have written on the board?
Oh, that thing.
Yeah. Do we really have two variables? Maybe we can eliminate one with this. Feels like the fence problem. Is h really just something that we can write anytime we want to in terms of x? Yeah, apparently if this is the area, the volume we have to have, h is just another name for 16,000 divided by x squared, right? Put that in there for h. So now we have a function for cost with the independent variable x. 6x squared plus, what is that, 3x times h. So sorry, 6x.
Wait, why 6x?
1.5 times 4, I just did it wrong. All right, so there's some simplification to do, but I think you're ready finally to do some calculus, right? Pre-calc demand is high. Geometry demand is high on these problems. I'm not going to go through the rest of this. Yeah, maybe.
We do that. Do I have to take still getting a negative.
I don't know where it is. I'll get back to you on that one. Okay. We're gonna let you. We'll come back later. So I just want to make sure we like kind of set up some of these and make sure you're in the right area. Huh? No. We're gonna keep going through it tomorrow. The homework tonight is still homework 6. And I want you to see if you can finish homework 6. Homework 7 is more optimization tomorrow. Okay. All right. So my goal is to try to expose you to as many different kinds of problems. They're all so interesting. They're all so interesting. Some of them have a geometric field. Some of them have, we're talking about area or cost or who knows what. All right, so are you comfortable with this picture? With this semicircle here? And the point 1 comma root 3 is maybe, I don't know, somewhere in here. Okay? So I want to know, how close does this curve come to this point? Like, what is the distance from this curve to this point? I don't think this is the closest point. Right here. Do you agree? What do you think it is? Let's take a guess before we get started.
There. Right above it.
Like there maybe or something? Something like that? Somewhere in here though, right? Maybe. And how would you, like if I said, no, I really think it's this one, how would you prove me wrong? What would you do? How would you actually, yeah, you would draw a segment, right? You can see that from the segment that it looks longer. How would you actually calculate the length of that segment though? Yeah. Yeah, the distance formula. Want to give it to me? Huh? Yeah, so let's actually say what it is in this context. It'd be, let's call this point right here, for now, xy. We'll come back and say something better in a second. This point, it could be here, we don't know, xy. We don't know where it is, but it's somewhere on this curve, xy. This point is not xy, it's 1 comma root 3, so there's no interesting things happening there. So what do? Take the difference of the x coordinates, x minus 1 squared, plus y minus root 3 squared. But of course y is this thing, right? So just notice here that we do in fact have an equation in only one independent variable. And distance is the thing that in this case we want to do what with?
Yeah, square root of 16 minus.
Oh yeah, sorry. Notice that this is the thing we want to minimize here, right? Don't we want the minimum distance that this could be? Find the x that makes this thing the smallest. Now, there is a hint that's provided here that will make your life quite a bit easier. If you were to measure the set of distances that all of us travel from home to school each day, and you were to list that, if you were the minimum distance on that list, what would happen if we squared all the distances? Guess what? Yours would still be, it wouldn't be the same value, but it would still be the lowest. So working with this equation is not real fun. It's also not fun to work with this one, but it's a little better. So feel free to just take the derivative of this thing on the right side instead. You're still going to have to multiply this out. It's still going to be really just terrible. Really just terrible. Okay? But feel free to just minimize that. It's at least a little less terrible than... Okay. I think you can do this one without a calculator. It's a little tricky. It's a little tough, but I think you can do it. It works out really, really nicely. I promise you that. All right, so, dude, yeah, eventually you may want to simplify first, but then take a derivative, set it equal to 0, the stuff we've been doing, the calculus. I leave for you.
And then you multiply these.
Yeah, multiply that all out.
And then
Maybe. I mean, I don't know. You could leave it as is. It'd just be a little messy. I might do some pre-calculus first before taking the derivative. These are a little intense. Yeah. Yes. Is the answer. And we've only given you like 7 problems or something, but they're like.
How long is it gonna take?
I don't know. Don't spend more than an hour on it. Oh look, there's my picture. I forgot I had a picture here. Here's the distance. Here's the up in bold the square distance. You can see that the minimum aligns to the same place. Okay.
Oh well, let's just watch the next one then. Okay.
What? Yeah, like I said, I'm just setting them up right now. We can come back and polish them off another time. I just want to make sure you're exposed to like lots of interesting different things that could happen. No, you don't like that idea? All right. 2 sides of a triangle have lengths A and B. Let's draw a triangle. Everybody calm down. Okay. And the angle between them is theta. Beautiful. What value of theta will maximize the triangle's area? No numbers in this problem. Can we take it?
No, it's a good thing I got it first.
What's the how do we compute the area of that triangle? Yeah, the area is equal to 1/2 base times the height, but the height is not pictured here. How do we calculate the height if we know A and theta? What's H?
Oh my God.
What's H? This is why we took trig, friends.
I don't remember.
A, what'd you say? Yes, A sine theta. Right? Or maybe you just remember this formula that it's 1/2 B times A times sine of theta, right? Is that a formula used in pre-calc? Remember that? 1/2 AB sine theta? Sine C? 1/2 AB sine C or something? Yeah. Right. But it comes from just from your 1/2. Anyway, the point is, here we go. Now, let me ask you this. This seems a little bit tricky because there's like no more information in the problem. Like, what recourse do we have? But what's true about A and B in this problem? I want to make sure we're clear. What's changing? What do we have free reign over? Theta. And that's all. A and B are constants. Right? So just have them come along for the ride here. They're just constants. If you want to replace them with like your favorite 2 numbers, that will work, right?
0 and 0.
Well, no, not that.
We do.
Alright, yeah, please leave your warm-ups here. Homework 6 tonight. Finish it tomorrow if you can. You need to skip a problem, or maybe even 2 if you're forgiven. But try your best to finish it. It's hard. It is hard.
So then
In your,
1/2 cosine. That's it? No. What do you do from there? Cosine of what equals 0? Pi. Is that the answer?
Friday.
True.
Is that part of the answer?
Oh wait, can I have my pen?
I mean, technically you still need to verify that it's a maximum.
parent meeting here in a second, so I might move you to another room, but we're set up here.